Welcome back my dear friends. A very good morning, good afternoon, good evening to all of you wherever you are in this part of the globe. And as you know, this is the DADM 3, which is Data Analysis and Decision Making 3 course under NPTEL MOOC series. And this total course duration is basically, if you consider the time span, is for 12 weeks, which when converted into number of hours is basically 30 hours in total, and total number of classes is 60, considering that each class is for half an hour. And as you can see from the slide, we are on the 19th lecture, which is the lecture on the 4th week, and after each week we have assignments, and we have already completed 3 assignments. So, we will be completing the 19th and the 20th lecture, and we will go for the 4th assignment. And in totality, as you know, there are 12 assignments, and after that set the whole course is over, you will basically take the final examination. Now, coming back to the last class, which is the 18th one, we were discussing that when you have the initial tableau means the initial matrix which you have. So, on the top one, I am just talking about the mechanical part, but obviously in between when I talk, I will talk about the conceptual framework, how you proceed. So, on the top portion you basically have the objective function, but consider the objective function is basically converted from the right hand to the left hand side. That is why the minus and plus sign concept will be repeated time and again. And in the initial tableau, on the top, the second the set of values of A would be corresponding to that basic feasible solution from where you want to start your iteration process, and the leftmost column would be basically the basic feasible solution corresponding to the fact for which the variables are non-zero. Now, in the initial problem which we considered, which they were a machine 1 and machine 2 with the constraint of 8 hours in each both the machines, the initial basic feasible solution was basically the variable slacks and the surplus, such that both of them were positive, because they were only 2. So, both of them were positive, which is basically a feasible solution, not the optimum one, but feasible solution based on which you can start. Now, for the maximization and the minimization problem, the concept was were very simple. In the maximization problem, you will take the maximum negative one, because they are on the left hand side. So, obviously, the minus sign would be considered, considering the fact that the maximum negative value would be the one where one addition of that particular decision variable would increase your objective function the maximum. Similarly, obviously, you will have the just the diametrical opposite rule for the minimization problem. And once you decide on the entering one, you have to also consider the exiting one. Exiting one would basically the one which will give you the maximum and the minimum for the ratios, in the sense that if you divide on the right hand side, which is the constraint maximum value, by the per unit time frame which you are taking, a per unit, because each decision variable which was the product to be produced in machine 1 and machine 2. So, their per addition would basically eat up into the resources which are the constraints. So, at what rate they are eating up would basically give you the maximum, the minimum value, based on which you will decide the exiting one. Now, the point where the entering and the exiting one basically means that is the pivot element. Based on that, you will slowly try to convert that matrix A into an identity matrix, and as you do that, you will get the values on the right hand side of the constraints, which will give you the final values of the decision variables. Whether x or s, that is a different question, and the value of z would basically give you the objective function, which is maximization or the minimization problem. Now, consider that there are different type of problems would be there, but what is the essence which we will be considering, that whether you have unbounded solution, whether you have basically multiple solutions, or whether you have unique solutions, that would depend on how your total iteration process leads to the final answer. So, consider these. So, you have an alternative optima for this case when the maximization is given by 4x1 plus 2x2, and the constraints which are given is basically 2x1 plus x2 less than equal to 8, and x1 plus x3 x2 is basically less than equal to 8. So, many solutions would basically mean the objective function remains fixed at a certain level, but the basic fully feasible solution would change. So, say for example, you are moving along the corner points, whatever the corner points in 2 dimension, 3 dimension, that does not matter. If you are moving from the corner points from the basic feasible solution, and they basically are trying to optimize. So, they would be at maybe more than 2 also, but minimum there are 2 corner points for which the objective function remains the same, even if the basic feasible the solution based on which you are getting this value of z at a fixed value may be different. So, in this case if you solve, I will come to the solutions later on. If you solve for the maximization problem, you will basically have 2 different corner points for which the objective function is fixed. And obviously, moving between these 2 points, obviously the exiting and the entering variables would give you the information that the objective function is not changing, but the corner points are different. Now, for the case when it is an unbounded solution, that means no bound on the solution, considering that the maximization is the problem which is given here, subject to constraints 2 x 1 plus x 2 is greater than 8 and x 1 plus 3 x 2 is greater than 8. In that case, as you keep moving the entering and the exiting one, the number of variables remain the fixed, they are not changing. So, in this case, say for example, if you had greater than sign for both of them, you will basically have x 1, x 2, S1 and S2, S1 and S2 depending on how we have been able to portray them as a slack or a surplus variable, depending on the greater than sign or the less than sign. So, as you judge the entering and the exiting variables, it would basically mean that the combination of the basic solutions would basically keep changing and the objective function will also be unbounded and it will keep on increasing, because that means you are going for the maximization problem, you are moving more away from the origin and moving more inside the first quadrant, such that the actual objective function basically becomes infinity. Now, in the case when basically you have the infeasible solution, the infeasible solution would basically mean that none of the corner points are basic feasible solution, hence the constraints would be such that the overall space based on which you will try to optimize would not be existing. Now, these 3 points we have repeated time and again, I will basically come to the problem solution when we consider this. Now, consider the minimization problem. So, in this case you have there are 4 constraints, the 4 constraints corresponding to the fact is that some of them both of them are greater than sign and 2 of them are less than sign. We will consider the S1, S2, S3, S4 as the slack and the surplus. So, the positive and negative values would basically mean that you are trying to be as you are less than types, hence adding to that constraint on the left hand side would make them exactly equal to 8 as in the first 2 constraints, and basically subtracting the value of S3 and S4 will basically, as they are greater than sign, it will bring them back to the value of 5 and 3 for the third and the fourth constraint. But as you are doing that, obviously your objective function, which was initially basically consisting of only 2 decision variables x 1 and x 2, would now become 2 x 1, which means per unit addition of x 1 would give you a cost or a profit factor of 2 units. Second point is 1 x 2, which means per unit increase in x 2 will increase your profit function for the objective function by 1 unit, and S 1, S 2, S 3, S 4, which are the slack and the surplus variables, as their overall combination or total contribution on the objective function is 0, hence each of them would be multiplied by the parameter or the constant value of 0. So, if you have the initial tableau, in that case, so I will basically draw. So, now remember this is a minimization problem. So, if you minimization problem, if you take into the minus on the left hand side, they become minus, but in that case you will consider the most positive value, remember that. So, obviously you will have W or Z and the values would be, you had basically x 1, x 2, S 1, S 2, S 3, S 4, and the corresponding values which you will have initially would be minus 2, minus 1, 0, 0, 0, 0, and the objective function would be here as already we know. Now, you basically have to think what is the basic feasible solution as you start. Now, pause here. If you put x 1 x 2 as 0 in this problem, then what you will have? You will basically have S 1 as 8, S 2 as 8, S 3 as minus 5 and S 4 as minus 5. Now, if you remember in the initial cases we have discussed that the initial basic feasible solution should not have any negative slack and surplus. In that case, what you can consider is that these points where you have S1 as positive 8, S2 as positive S3 and S4 as negative 5 and negative 3 respectively, would not be a basic feasible solution, it will be a basic infeasible solution. I am going to come to that later with an example. So, obviously, without going to the general details. So, in this case you will basically have a 6 dimension problem, in the sense you are considering S1, S2, S3, S4, X1 and X2. So, based on that you will consider that what is the basic feasible solution, and based on the basic feasible solution you will, what you will basically aim at is that you will start with A, and the right hand side you have basically B. Let me use a different color. So, you will basically have B, and the x would be on the leftmost column, then you will keep multiplying and considering the exiting and the entering variables would be based on the fact that is a minimization problem. So, in the minimization problem obviously you look at the least negative, and the one going out would basically be pulling down in the increasing or pulling down the objective function in the least possible manner, because of the minimization problem. So, as you convert A into an identity matrix row by column by column, you will basically ensure that the actual x values which you will have, based on which you will try to solve the problem, would be the ultimate values of the x's, which will give you the best possible solution, which is the optimum solution. On the right hand side, the values of B would be such, the top value would basically give you the minimization value of W in this case, because it is not Z, and the other values would be corresponding to the basic feasible solutions of the x1 and x2 which you have. Now, remember one thing, in case if your final solution is only pertaining to x1 and x2, which would mean that S1, S2, S3, S4 would all be 0, technically it would mean the constraint 1, 2, 3, 4 has been utilized in such a way that maximum utilization is possible from x1 and x2, such there is no surplus, no slacks variables which are left, because their actual contribution in the objective function obviously vanishes, because they are all 0, and in the constraint also there would not be any leftovers. Now, consider that you want to basically solve this problem, and you are going to solve this problem in such a way that these initial conditions where the basic feasible solution would have all the surplus and slacks as, say for example, positive. So, in order to ensure that, you will basically consider the big M method. Big M method means, that means you are adding some variables or some values to such an extent. So, they are so large in value that the overall effect which you will have from the slack or the surplus would basically be negated. So, let me consider this problem. So, this is the same problem which you had considered. The solution methods would only change corresponding to the fact that the number of the tableau would basically increase in size. How it will increase in size, I will come to that later. So, in this case you have the minimization problem, as the red color shows, it will be 2x1 plus x2 plus 0x1 plus 0s2 plus 0s3 and plus 0s4, where s1, s2, s3, s4 are the slacks and the surplus. Now, in the constraints which you have already seen, the first two constraints had s1 and s2 as positive, because if you had s1, x1 and x2 as 0, then the value corresponding to s1 and s2 would have been 8, because here the constraints are 2x1 plus x2 was basically less than equal to 8. So, adding up s1 would basically make it exactly equal to 8. The second constraint was x1 plus 3x2 was less than equal to 8. So, adding s2 would basically make it equal to 8. Now, the other two constraints was like this, you had 2x1 plus 2x2 was greater than 5, and x1 plus 3x2 was greater than equal to 3. So, adding in the negative sense s3 and s4 would basically make them exactly equal to 5 and 3, but those values would be negative. So, in order to overcome that, you add the artificial variables which are given by the symbol of a1 and a2 corresponding to the third and the fourth constraint. Now, as you are adding the artificial variables a1 and a2, they would automatically come into the objective function, because as you change the constraint, the technically the objective function would also change in its characteristics, even if the effect of those artificial variables and the slack and the surplus in the long run would definitely be 0. So, your minimization problem now becomes 2x1 plus x2 and S1, S2, S3, S4 had 0 values in their parameters. So, it is 0 S1 plus 0 S2 plus 0 S3 and 0 S4, and these values of artificial variables which I will consider to be effect to be very large, such that we multiply them by a very large number m. So, it will be m A1 plus m A2, and in the long run their values of A1 A2 should be 0, because their overall effect in the objective function will be 0, considering even if m1 and m2 are very large. So, the big M method actually means that you are basically adding up a huge amount of value onto the artificial variables, such that in the they are artificial. So, such that in the long run their overall effect when the problem is solved basically becomes 0. Now, when you start off this problem, you will basically have S1 and S2 as the slacks, because you are adding them, S3 and S4 as surplus, because you are negating them, that trying to reduce the third and the fourth constraints, and A1 A2 are the artificial variables which have been added to the third and the fourth constraints. So, the tableau when you look at would basically be accordingly. So, the first equation would be 2 x1 plus x2 plus S1 plus 0 into S2 plus 0 into S3 plus 0 into S4 plus 0 into A1 plus 0 into A2 is equal to 8. Second one would be, I am not writing it, I am repeating it again. So, the first would be 2 x1 plus x2 plus 1 into S1, because that is already there, plus 0 into S2 plus 0 into S3 plus 0 into S4, that completes all the slacks and the surpluses. Then the artificial variables will come, which will be 0 into A1 plus 0 into A2 is equal to 8. Similarly, in the same way and same logic, the second constraint would be x1 plus 3 x2 plus 0 into S1, because S1 is not there, plus 1 into S2 plus 0 into S3 plus 0 into S4 plus 0 into A1 plus 0 into A2 is equal to 8. Similarly, the third constraint would be x1 plus 2x1 plus x2 plus 0 into S1 plus 0 into S2, because S1 and S2 are not corresponding to the third constraint. Continuing reading, it will be minus S3 plus 0 into S4 plus A1 plus 1 into A1 plus 0 into A2 is equal to 5. And finally, the last constraints would be, the fourth constraint would be x1 plus 3 into 1 into x1 plus 3 into x2 plus 0 into S1 plus 0 into S2 plus 0 into S3, that means S1, S2, S3 corresponding to the first, second, third. Continuing reading, it would be minus 1 into S4 plus 0 into A1, because A1 is basically corresponding to the artificial variable in the third constraint, and finally it would be plus 1 into A2 is equal to 5. So, when you have this actual basic feasible solutions, basic feasible solution basically would be a vector consisting of x1, x2, S1, S2, S3, S4, A1, A2. So, all the combinations which you will have would basically give you the feasible solution, some would be basic feasible solution and rest would be basic infeasible solution. So, we will basically take one of the basic feasible solution and basically proceed in the same direction, that for the maximization problem we will consider the most negative, and the minimization problem we will just do the 180 degrees apart, we will take the other direction, and then the exiting one also would give you the pivot element. Based on the pivot element, we will basically slowly be converting that matrix A into an identity matrix. As you do that, the value of the B on the right hand side would give you the actual values at the optimum point, and it will also give you the value of Z or W depending on whether it is a maximization problem or the minimization problem. Now, there would be a considering the problem, I had mentioned that very briefly, but I will come to that. So, whenever you are solving a problem, like you are looking at a mirror image, say for example, the mirror is in front of you, and consider that. So, technically we know from basic physics, it is nothing to do with the optimization problem which I am considering from basic physics, that you are a real object, and the image which is forming, considering is a simple plane mirror, is basically a virtual image. Now, as you start moving towards the mirror, so the virtual image also starts moving towards you. So, consider in this way that you want to reach an optimum point. So, you are trying to basically consider the problem as a maximization problem. So, trying to maximize the problem also means that you are slowly increasing the values of x 1 and x 2 and the z values also increase. But let us consider the problem on an other scale, that means you are looking from the negative direction. So, minus on an of a maximization problem actually means a minimization problem. So, now what you will try to do is that, and why this is done, it will be very clear depending on the number of constraints and number of the objective functions which you have. So, now consider that if you have basically a maximization problem, what you will try to do is that you will try to basically convert it using simple converting the constraints into a decision variables and the decision variable number of decision variables into a constraint. You will convert that primary problem into a dual problem, and trying to basically solve the maximization problem in the primal problem would also basically mean that you are trying to solve the minimization in the dual problem, which means that at the conversion point the maximization of your primal problem would be equivalent to the minimization of the dual problem, which is minimization. And if you consider the other way around, if you are trying to minimize a minimization problem and trying to basically find it out, then its dual would basically be the counterpart, which is the maximization of the dual problem. So, technically what we are trying to do is like this. So, consider this is the line, whatever the objective function is, and I want to reach here. So, I can basically reach it in two ways. In the maximization problem, I start from a lower level, and keep increasing and changing my decision variable such that at the optimum point I reach the maximum and stop my solution. From the minimization problem, which is the counterpart, I will basically start from the other side and try to decrease the objective function considering the combination of decision variables. Now, remember the decision variables which are there in the objective function or decision variables which are there for the maximum problem need not be the decision variables which are there in the minimization problem. So, in the minimization problem I will basically consider as other set of decision variables, but they have a relationship. I will basically decrease my objective function, try to reach such that at the optimum point the objective function of both of them would be exactly the same 0.1, and the point at which I will obtain that objective function maximization and minimization would be the same. That means, the optimum physical point or feasible point or the corner point where I will basically stop my optimization problem would be the same. Now, what would happen is that my number of decision variables would be considered, the numbers, not the exact what we are taking, that is not the issue. The number of decision variables which we have in the maximization problem would be considered as the constraints, and the number of constraints we have for the maximization problem would be considered as the variables. Now, you just reverse that when you are taking the minimization problem, the exact concept remains also the same. That means, the number of decision variables now becomes the constraints, and the constraints now basically becomes the decision variables. Why it is done is that consider you have a optimization problem where the number of decision variables is very large, but the constraint is very small, or on the other hand consider the number of decision variables is very small, but the constraints are very large in number. So, trying to solve a problem where number of constraints is very large or the number of decision is very large may be difficult to solve when you are trying to basically do the problem mathematically, such that converting that into a dual would be easier for you to solve conceptually, which means that when you start the tableau, in one case the tableau would be m cross n, where the m size may be very high and n may be very small, and in another case the n size may be very high and m size may be very small, depending on how you basically tackle the problem. So, in the primal maximization problem, if your objective is basically to minimization 1, the primal minimization problem would basically be the maximization problem, which is the counterpart 0.1. Another point we should basically measure is that if the constraints in the dual problem, in the primal problem are greater than sign, then the constraint would just be the reverse. That means, greater than sign will be replaced by less than sign and less than sign would be replaced by the greater than sign. and the variables of the signs would also change. In the case when they are greater than equal to 0 or less than equal to 0, basically they would dictate that what is the sign of the variable. So, in case if you are reading along the row, the primal problem is the maximization problem. So, in the dual case it will be a minimization problem. The constraint of greater than sign and the variable sign, if they are greater than equal to, would basically be converted into unrestricted. Unrestricted means that both x and x can be greater than 0 and less than 0. In the primal problem, when it is the minimization problem, the counterpart of the dual problem would be maximization 1. For the dual problem, the less than sign gets replaced by the greater than sign, and greater than sign gets replaced by the less than sign, and again the variable sign would basically be now unconstrained or unrestricted, depending on how you have basically been able to formulate the problem. So, let us consider the problems accordingly. So, consider the primal problem is there. Solution techniques again they remain the same, only the primal dual problems are being considered, such that considering the number of constraints and number of variables are there, one is preponderantly high or the value is very high, then the primal can be converted into a dual and vice versa. That means, if I am looking at the mirror and I am basically proceeding to that, the objective function, if it is a maximization problem, will keep increasing, and from the other side it will basically keep decreasing till the point where they merge and the value exactly becomes the same. So, the primal problem would basically have, consider it is maximization problem, and the variables are x 1 and x 2. We have not considered the surplus and the slacks. So, your objective function is 3 x 1 plus 2 x 2, you want to basically maximize it, and the constraints are of this type. It is 2 x 1 plus x 2 is less than 8, and x 1 plus 3 x 2 is less than 8. So, in this case, as you add up the slacks and the surpluses, it actually becomes like this. Your actual problem basically becomes objective function becomes 3 x 1 plus 2 x 2 plus 0 s 1 plus 0 s 2, because these are the surplus and the slacks, and in the constraints you have 2 x 1 plus 1 x 2 plus 1 x s 1, because that is the slack and the surplus depending on whether it is greater than or less than sign corresponding to the first constraint, and the second constraint has a slack or a surplus of s 2, that is why it is shown green in color. So, it will be 2 x 1 plus x 2 plus 1 in s 1 plus 0 s 2 is equal to 8, because you are trying to balance both the sides of the equation, and the second constraint would be x 1 plus 3 x 2. Here s 1 is not there, so it will be multiplied by 0. So, it will be plus 0 s 1, and the last variable which will be there for the second constraint will be s 1 1 into s 2 sorry 1 into s 2, that is the slack surplus for the second constraint is equal to 8. And here you will basically consider that as you are converting the primal into dual problem, you will basically converting the constraints into the variables and the variables to the constraints. With this I will end the 19th lecture and I will continue more discussion on the primal dual problem and the formulations later in the 20th class. Have a nice day and thank you very much.